Okay, so now we have question 6, analysis of machines, or section 6.4. So the question is, at the gym, Jimmy's working out with a pulley system. He looks at the machine after adding a weight of 50 kilograms to the end of the cable. What is the magnitude of forces at point E? Now keep in mind, he has not yet actually done any lifting, so he's not adding any force. He's not adding any force in this direction yet. It's completely empty there. So what we're first going to have to do is we're going to try to figure out our forces at point E. So the first thing I'm going to look at is I'm going to try to figure out how I can start solving for E and everything like that. So I'm going to add in my reaction forces, which are here. You have A, Y, A, X. You also have B, Y, and B, X. Along with that, you're going to also have all of these forces coming off E, because that is where the joint is. And you're going to take this 50, because it's 50 kilograms here, and we're actually going to multiply that by gravity to get its force in newtons. So now from here, I'm going to try to be solving for E, and what I think I want to do is I'm going to be breaking this machine apart by its different sections and parts. So first, I guess we'd have a section. First things first, why don't we break it up some? So we're going to break up and use this bar from A to D. Just going to use this real quick to try to make the lines a little nicer. So that's my bar from A to D. Now here we have point A, point D, and point E. So now here we're also going to have A sub X, A sub Y, E sub Y, E sub X, and up here we're going to have D sub X and D sub Y. We're now going to also draw out our other shape, just so that way we can compare. Okay, so this would be our shape from B, E to this top point right here. That doesn't have a name. So we got B, we have that point, and then we have E. So I've already drawn my forces up here for E going in those two directions. So I'm going to draw them in the opposite direction this time. So we got EY. Now here, this way, we got E sub X. Up here, we have the tension pulling on. We have tension pulling from up there, which is just simply T, which equals, of course, 50. 50. And then at B, we have B sub X. And, oops, that was bad. And horizontally, B sub Y up here. And B sub X. So after looking at my two different shapes, I'm going to choose this shape right here. Simply because when I look at it, I have less unknowns, and I can actually get rid of some of my unknowns. So my first move will be to try to find my to try to find my E sub y value, because when I look at this, when I look at it, it's pretty solvable if we take into account and think about how we'd solve these. So when we go about it, it would be our sigma f sub y equals 0, because we're trying to find e sub y. So if we do this, we're only going to have two unknowns. We're going to have b sub y plus, b sub y minus e sub y equals 0. So now we run into an issue though, where we don't know b sub y. So what I'm actually going to do is I'm going to go back to this diagram that we have right here, and I'm going to do a moment about point A, because when I do a moment about point A, I'm getting rid of the effects on point A here, getting rid of these, and the forces at E won't matter because they're equal in all directions. So therefore I can go sigma of moment of point A, and I'm just going to call this diagram I, this diagram I, and this diagram I, just so that way it's a little easier to distinguish between each one. So this would be f of I. And so now I'm going to do my moment about A. So when I do my moment about A, and this all equals 0, of course, my A values are gone. And now because my BX value is at the same level of plane, it doesn't have any increase or decrease in the y-axis, that one also gets ignored because it doesn't have any change. So that simply leaves b sub y, and it's positive because it's creating a force in a counterclockwise direction. And then we have our T value up here, our tension caused by our cable and everything. So when we do this out, it's going to then be, because that's creating a force in the clockwise direction, it's going to be minus. And of course, it's 50 times 9.8. And now we're going to look at the distances and add those in to be multiplied by it. So if we look here, the difference between point A and point B is 1.5. So I'm actually going to do 1.5 times B. I'm now going to look here, and if I notice, I have that the force from cable, the force of the cable is coming down from point D. If I look at point D, it's at 1.5 plus 1. So 1.5 plus 1 equals 2.5. So that tells me that I then multiply this by 2.5. And this all equals 0. So now I'm going to multiply all of this out. And when I multiply all this out, I get 1.5 by minus 1,225 equals 0. So what I'm going to do is I'm going to add 1,225 to the other side and divide it by 1.5. So that I can write it out like this too. So of course, with 0 divided by 1.5 still 0. And then I'm going to add this to the other side. When I do that, I'll end up getting by equals about 816.667. I can now take this b sub y value and I can plug it in to my original equation up here. So that tells me I get 816.667. Sorry, that was supposed to be a 6, but it just doesn't look right. 667 minus e sub y equals 0. This tells me then that e sub y equals 816.667. Now, if I look, this is a positive number, which means we properly assumed that in this diagram, for E sub y was downwards. So that means it's 816.667 downwards. Well, newtons downwards. So now we're going to start solving for E sub x. Now, E sub x, if I look at, I can do a little simpler because I can go directly to this diagram 3 again. And in doing so, I can do another moment. I can do another moment because E sub x creates a force and creates a force that's actually different than that's going to be different than 0. And I can, and what makes sense is because I do have 3 variables affecting the x. One of them I know, and one of them I can get rid of by simply doing the moment about that point. So if I do sigma of the moment about B from diagram 3, and when I do that out, this equals, I have to use my change in distance from here to there, which in the problem is listed as 2 meters, as well as my distance from here to there, which in the problem is 1 meter. Well, I'm aware that this is not the most accurately drawn diagram. This is what it is up here in diagram 1. So now using this, I can take my moment about B of diagram 3, and when I do this, I'm going to do, this should equal 0. So, but I'm going to do my distance from the point where I'm taking my moment from times my value of E sub x. And I'm going to, because that's creating a force in a counterclockwise direction. That's why it's positive. Now my tension is going to be in a clockwise direction. And here it's going to be this 2 plus 1, which gives me 3 meters away from point B. So this would be minus 3 times t, and this should all equal 0. So now I'm going to plug in my value for t. So that would be 2e sub x minus 3 times 50 equals 0. So I'm going to add my 3 times 50 to the other side and multiply it out. Now 3 times 50 is 150. So that tells me it's 2e to the x equals 150. I divide both sides by 2, and that gets me e to the x equals 75 newtons. And again, it's positive, which means we assumed correctly that it was to the left. So that means it's 75 newtons to the left. However, this problem wants to know the magnitude of forces at point E. So because it wants to know the magnitude of forces at point E, we're not done yet. We actually have to first find basically our reaction at point E. So our reaction at point E is going to equal the square root of our E sub x squared, so our 75 squared, plus our E sub y squared, which would be 816.667 squared. Now, when I actually multiply this out and plug this into my calculator, what you're going to end up getting is about 820.10 newtons, which means the magnitude of forces at point E is 820.1 newtons, which then leaves you with this as your answer. Thank you.